Okay, a proof by cases of a universal statement okay, for all statement, for all x, p of x occurs, breaks the domain for the variable x into different classes and gives a different proof for each class. The proof for each class is called a case. Okay, comma, the comma. And every value in the domain must be included in at least one class. Okay, so we're partitioning the domain. Okay, example one. Okay, prove the theorem by cases. Theorem. Okay, for every integer x, x squared minus x is an even integer. Okay, so we're going to have two cases, right? We're going to first prove that this is even if we start with an even, and then we're going to prove that it's even if we start with an odd. Okay, so case one, assume x is even. Okay, or is an even integer, I guess I should say. Okay, since x is even, there exists k, an element of z, such that x equals 2k, right? Okay, plugging 2k in to x squared minus x gives 2k squared minus 2k, which is equal to 4k squared minus 2k, which I can pull a 2 out of. Factor a 2 out of, I get, not 4, I get 2k squared minus 2k, which shows that it is an even value. Okay, since k is an integer, then 2k squared minus 2k is also an integer. Just erase. And thus x squared minus x is an even integer. Okay. Okay, so that's case 1 proven. X is even. Okay, case 2 is assume x is odd. Okay. Okay, then since x is odd, there is an integer, k, an element of z, such that x is equal to 2k plus 1. Okay, plugging in into x squared minus x, well, x squared minus x, it gives 2k plus 1 squared minus 2k plus 1. Well, this thing is going to be 4k squared plus 4k plus 1 minus 2k plus 1, which is 4k squared plus 4k plus 1 minus 2k minus 1. The 1s are going to cancel. So we're left with 4k squared plus 4k minus 2k. And that I can pull a 2 out of. 2k squared did I mess up? Where's k? Oh, I didn't subtract the. No, that's that. Okay, this is. Oh, that should be a k. Okay, minus k. There we go. And so this is 2k squared plus k times 2. K squared plus k. Okay. Since k is an integer, then 2k squared plus k is also an integer. And thus x is even. Sorry, it should be x squared. This x squared minus x is even. Okay, so both roads led to even values. Okay, because we could both pull out a 2 out of each of them. So we're good. Okay. Sometimes sometimes the proofs, I should say, for two different cases are so similar that it is repetitive to include both cases. The term without loss of generalization, or generality, I should say, without loss of generality, or abbreviated WLOG, WLOG, okay, is used to narrow the proof to one case. In order to generalize to all cases. Okay. Okay. So example 2. Okay, prove the theorem. Okay, if two integers have different parity, that is, that if one is even and the other is odd, or if one is odd and the other is even, then x plus y is an odd number. We're saying that if we add an odd to an even, we get an odd. Okay? Two evens make an even, two odds make an even, but an even and odd make an odd. Okay. So instead of letting x be even and y be odd, or letting y be even and then x is odd, doing two separate cases, we're just going to do one case because x could either be even or odd, and the other case is basically identical. Y could be either even and odd, but you could let x be y and y be x. It really doesn't matter in this case. It's just if one is odd, the other has to be even. We don't really care which is which, as long as one is odd and one is even. So we can say the proof without loss of generality let x be even I'll say let x be an even integer, and y be an odd integer. Since x is even, there exists an m such that x is equal to 2, and I should say an integer m, okay, such that x is equal to 2m. Since y is an odd integer, there exists a j such that y equals 2j plus 1. Again, I should say an integer j. I don't know why I always do that. An integer j such that y is equal to 2j. If we add these together, adding x plus y and plugging in, we obtain 2m plus 2j plus 1, which is equal to 2 times m plus j plus 1. Okay, where m plus j is the sum of two integers, which is also an integer. Since m and j are integers, their sum is also an integer, and therefore x plus y is an odd number by the definition of odd. Okay. Okay. And again, we could have broken it up into two cases, let x be even, y be odd, and then let x be odd and y be even, but it wasn't necessary. Okay. Without loss of generalization, we can combine two cases into one. Okay. Okay, and with that, that is 3.7. So